Kenwood at the McLeod Family Vineyards for the past 3 years, and we've been doing both soil health examination and soil moisture, and we're asking a lot of the same questions that Patty has, which is part of how I found Patty. And so I'm going to take you through what we have done, and so I'm going to take about 5-10 minutes to intro what the project is, and then we're going to hear from Dr. Josh Beniston, who is the soil scientist we've been working with, and we'll hear about the results he's found from our soil sampling we did at the beginning and end of the trial. And then we're going to hear from Dr. Mark Greenspan, who has worked with us to analyze the soil moisture data that we have from the trial. And then after that, they'll both speak for about 10 minutes each, and then we'll have a question and answer period of 5 to 10 minutes after that. So feel free to keep shooting your questions at us. Those were great questions, and Kate will take those, so that's what we'll do the last 10 minutes. So what was the purpose of our field trial? We wanted to investigate the 3 primary vineyard tractor row tillage management systems that we see here. I go out to a lot of different vineyards. There's a fair amount of full till. I think the most common has become alternate row till, and there's a number of people interested in no-till, and you're seeing more and more of that. Certainly, I think that's been more common in hillside systems, but we're starting to see that more in general. And so we had some questions that were coming up. I was doing my irrigation evaluations, working on LandSmart plans, and people were talking about how they managed it, and there was a lot of interest and passion about their particular management style. So there were people who say you got to till because otherwise you're going to lose the moisture, competition for both water and nutrients. And then there was equal passion for people who weren't tilling, that were saying you can't till because then you lose organic matter, and organic matter holds water, and that's a problem. So I wanted to start, I and others who were talking about this, both viticulturists and other folks in the field, we wanted to really start to drill into what is the answer there, and get away from anecdotal sort of experience, but more like, what does the data tell us? And so a primary question, really was, which of those systems retains more water in the soil, and which has the potential to conserve the most water? And also then, which has the greatest soil health impact? So we got a grant from NRCS that allowed us to explore this, and then we got going. We started in 2016, but I will first say that the question of water in the soil is that these things that are out there in studies, have told us that organic matter holds roughly 18 to 20 times its weight in water, and that for every 1% increase in organic matter, we see an additional acre inch of water. So an acre inch is 1 inch covering a whole acre, and so an acre inch of water is also 27,154. So I've seen different literature. You see anywhere from 20,000 gallons per acre to 1 acre inch being 27,154. And it will obviously vary in different conditions, different soils. So we designed the project. We found a grower, John McLeod, whose family's ranch is in Kenwood, and they've had vines probably since the early 70s, I'm guessing. He was very interested in this question, as well as us, and he wanted to explore these questions, and we'd already been in touch with Dr. Josh Beniston, who we'll hear from in a minute, and Josh, had a big interest in this too, and said, yeah, let's look at this. So we went out to the ranch. We identified a place on the ranch that was suitable for this type of study. It is in Kenwood, and that's the Mayacamas, where soils can be quite variable and you get the volcanic soils. But we did find a portion of the ranch that was pretty uniform and looked good. So we decided to move, we moved ahead, we got the grant funding, and then Dr. Beniston designed the field study. And this is, that's a picture there of when we were laying out the plots. So what we did is we created 100-foot long plots. To have the uniform soil, we had to stay within a given area. So we created 100-foot long plots, then a 10-foot break, and then another 100-foot plat, and then there'd be another 100-foot section. So we created 3 repetitions to make it scientifically hold up. We needed 3 repetitions of the 3 different tillage management systems. So those are no-till, full-till, and alternate row-till. Here's a site layout map from above that you can see. So 3 different colors. Each color is one of those tillage management spots. So you can see it's all pretty tight. That if I were to do another demo study, it'd be good to have full rows in one management. That did create some challenges along the way, but this is the field layout, and that's what we went with and pursued throughout the project. So when we put the tillage treatments in place, it was fall 2017. It was right after the fire. The fire actually burned 150 feet away from this, so the project was in danger right as we were about to start, but we got it in. We had to manually put the cover crop in. I broadcast it with a manual spreader, and as the first rain was starting to come down in 2017. We used OSB plow down from LaBallesters, which a lot of growers used, at 50 pounds an acre. Tillage treatments were implemented each spring and fall through spring 2019. And then alternate row plots switched which side was tilled and which side was mowed in spring as well. We did soil sampling starting in 2017 before we implemented the treatments. We did it at 3 different depths, 0 to 10 centimeters, 10 to 20, and 20 to 40. And we took 3 and 4 subsamples on each side of the road to create a sample. So each side of the row would be a different test that we submitted to the OSU lab. And we were looking at active carbon, total carbon, nitrogen, water aggregate stability. And then we did all the tests again last fall, 2019, and then we added available water capacity at that. But we did leave the 20 to 40 centimeter out because that was really hard to get at, and some of the part of the site, the bedrock, is only a couple feet deep. So it made more sense to go with the other depths, and that is where most of the activity that we're looking for is. So we also had the bulk density samples analyzed at the Santa Rosa Junior College lab, and got those results in the past few months. So we worked with Dr. Greenspan to do the soil moisture content and look at that. We put in AquaCheck probes that range from 2.5 to 4 feet deep. We installed them in February of 2018, and for 2 full seasons, we measured that data with that data logger and a probe you can see in the picture. So I had to go out every 2 to 4 weeks and take those measurements. The probes read every 8 inches, and we ended up focusing on the 30 and 60 centimeter level, which Dr. Greenspan will talk about. He analyzed the data in 2018 and 19. So here's a soil moisture curve. You can see this is what, when we take the readings and we look at the web interface, this is telling us when it rises up. This is an irrigation event in this case, but then we were looking at the drawdown in the spring is what we ended up focusing on from natural rain events. So we shared the information with everyone. We had a big workshop in June out in the field, and we will be doing a June workshop at Jackson Family Winery, Sara Lee Vineyard, where we'll be talking about this and the results from there. And we will continue to share these results as we have opportunities to do so. Here is a few nice pictures of the vineyard, and with that, I'm going to let the scientists on the project talk about what they see from the results. And here's my information if you want to get in touch with me. So we're going to transition now to Dr. Beniston. So Dr. Josh Beniston teaches soil science and coordinates the Sustainable Agriculture Education Program at the Santa Rosa Junior College. He has a PhD in soil science from Ohio State University, where he conducted research on soil carbon at the Carbon Management and Sequestration Center. Prior to the SRJC, he was a research scientist at the USDA Agricultural Research Service. Dr. Beniston has supported soil health research and education projects throughout Sonoma County and has surveyed soils for vineyard development and management in several locations.
Okay, good morning, everybody. Thank you for having me, and thank you to everybody who is tuning in with us out there and interested. And thank you to the Sonoma County wine growers for making it possible to do this today. So I really am just going to dive into the soil results that we got from the soil sampling we did this fall at this tillage and soil water trial that Keith described here in the Sonoma Valley. And so I'll take just a quick look at the soil conditions at this research site. What kind of soil was it? I'll go over the soil sampling briefly that Keith described as well. And then we'll get into some results. We will take a look at some numbers. So my talk will be fairly quick and very heavy on numbers, but we'll take a look. So this, as Keith mentioned, we were up on the mountainside here in this vineyard for the trial, but we were able to find a nice little bench area of head-trained vines, and it was a uniform spot for the farm that was this Laniger soil series, which is fairly common in the North Bay. It was a very rocky or very gravelly soil, according to the NRCS standards. Lots of rocks, large and small, at the site. But it was a very nice soil. It had a loam texture class, and it had right around 4% organic matter or 2% carbon throughout. So a very nice soil really for any kind of farming if you can deal with the rocks. And so Keith described this, so I'll just say briefly that we collected samples both in the spring of 2017 and then just at the tail end of this past fall in November and December. And the data that I'll show are from these top two depths, 0 to 10 centimeters or 10 to 20 centimeters. And the plots, the research plots with the tillage were on both sides of a single row of vines. And so we collected soil out of both of those sides, and we mixed it together. For any of these plots, we were collecting soil from multiple soil samples and mixing them together. And so jumping into the results, the big one that stands out for this data set and one of the things that we're probably most interested in and growers may be most interested in is the carbon or the organic matter. And so this was the most statistically separated data that we collected from the soil properties at the site. And so on the graph here, I have one bar for the fully no-till treatment and one bar for the treatment that got tilled on both sides. And it was basically two full growing seasons of management. And so 2 full growing seasons of management ended up with about a 13% reduction in carbon in the soils that were getting full tillage. And if I add in the third treatment, the alternate row treatment, that one, the measurement tended to be much closer to the plots that we were not tilling. So the real difference in this carbon data was the plots that were getting tilled on both sides for both years. They showed actually a measurable decline in these data. So that is significant and does speak toward the other two management practices of not tilling or doing it alternate years as being better for preserving organic matter in our climate. And so, and I would say in this study, I don't recall if Keith mentioned it, the alternate row treatment was flipped each year. So one year it got tilled and one year it didn't. And we collected soil and mixed it from both of those. Looking at the carbon data from both depths, there was no difference really between the treatments at the lower depth. All of the action was there in the top 10 centimeters. And when we actually went out and looked at the soil right after they had been disking, which was the primary tillage, the disc was going about 4 inches in the soil. So top 10 centimeters was really where the disturbance in the tillage was happening. Some other soil results. We looked at this water stable aggregate measurement where aggregates from the soil are separated out and put under a device in the lab that you see on the screen that's basically creating droplets that are the size and shape and carry the physical impact of raindrops. So that's a rainfall simulator raining down on soil samples. And the idea here is to see if the structure of the soil is resilient and resistant to rainfall and holds up. And this is considered widely accepted as a valuable measure of soil health. And so, again, we didn't, the numbers here again show a reduction, that with the full tillage we could measure a reduction in the water stable aggregates in the top 10 centimeters of these plots compared with the no-till treatment. And very similarly to the previous data, the carbon data, we find that the alternate row treatment is very similar to the no-till treatment. So alternating rows was again preserving the structure of the soil in these treatments. And now it looks like I'm into Mark's slides. So the other data that I was going to present were to show that we took also some measurements on something called active carbon, which is being promoted a lot as a soil health indicator, an early indicator of change. And in this data set, that didn't show, we didn't see any difference between these treatments with that active carbon measurement. It wasn't effective at showing differences in these data. We also spent a lot of time measuring the bulk density of the soil, which tells us the pore space and tells us the degree or not degree of compaction at the site. All of these treatments had very nice bulk density and porosity measurements, and there was no difference among the treatments for the bulk density. And so what I had in here to wrap up with these data were that the big results were that we found, these reductions in aggregation, which is like I think a 24-25% reduction in water stable aggregates after 2 years of tilling every year, and a 13% reduction in the carbon. And so that begins to add up if you're doing that. We just did this for 2 full growing seasons, and so we don't know how far out into the future that trend would continue, but it is a significant drop for just a couple of years. Some challenges that we found in these data sets were that we only had 3 plots, which there's a balance between getting better data with more plots or just the practicality of managing it. I don't know that we could have managed many more plots in the field. We're learning quickly that on-farm tillage experiments are cumbersome and challenging to manage. Other treatments maybe not so much, but tillage very tricky. And I was surprised that we were able to see the change that we did after just 2 growing seasons. That's a short time in the world of the soil for things to change. And then lastly, I'd just conclude that an interesting result here is that managing the soil such that it's getting tilled 1 year and then not tilled the next year and is being left in vegetative cover the next year, these data seem to show that is really preserving soil health as well as not tilling. So that seems to be a very effective strategy for soil conservation as far as these data are concerned. And with that, I'll wrap up for now and turn it over to Dr. Greenspan.
We do have one question for you.
Sure.
In a warmer climate, would you expect more carbon losses associated with the tillage?
Yeah, that is that's what we know from studying soil carbon around the planet, is that higher temperatures and higher precipitation mean you get more decomposition and things break down faster. And so, so yeah, in general, warmer climates, things tend to deplete quicker.
We're going to hear now from Dr. Mark Greenspan. He is a viticulturist who founded Advanced Viticulture 15 years ago. It's a growing business based in Windsor. This company delivers multifaceted vineyard consulting with an emphasis on water and nutrient management, provides vineyard technologies and automation, and is a full-service vineyard management and development company for high-end operations. Dr. Greenspan has a MS in viticulture and a PhD in agricultural engineering, both from UC Davis. Thank you, Mark.
Thanks, Keith. Good morning, everybody. I'm happy to be here talking to this camera. I'd rather talk to an audience, but this is going to work fine for now. So yeah, I was involved with this at the beginning, and I was involved with this at the end, but not a whole lot in the middle. But my analysis is pretty much a post facto kind of thing. It's going to try to go through this really quickly because I have like way too many slides here to show you in my time. It's already been introduced. We used these AquaCheck probes. They were installed under the vines in the vine row, like Patty had in her trial. Each of these probes has 6 sensors, but we only looked at 2 depths. The reason being is, as Keith mentioned, these soils varied in depth quite a bit. And so we had to try to normalize it as much as possible across the field. And we chose two particular depths to study. And those 2 depths, again, were 30 centimeters and 60 centimeters, about 1 foot and 2 feet. Nice and convenient there. And the fact is, we found different effects at both those depths. Without further ado, I'll just go into the discussion. I wanted to show this. This is just a snapshot of some raw data from a water soil moisture probe. It's actually not from this trial. I just put this in here as a screenshot from that I had. But it's the same type of data we're looking at. This is an AquaCheck probe. It's reporting continuously, roughly every half hour. I think it's exactly every half hour at 6 depths here. And you see 6 depths, each one's a different color. Anywhere, this particular probe is a 40-inch probe that we're looking at. Not important, but I want to just show you what we're looking at and analyzing. The scale on the y-axis is relative water content. It's not volumetric, it's not calibrated, which is fine. It's how I normally use them. We did a little bit of manipulation to the data only to make them normalized across the different plots. So what I wanted to do is not change the scaling of them, but shift the data so they were started at the same moisture content, relative water content. That's all we did as far as the manipulation of the data. And what I did, we had 9 plots with 3 reps of each treatment. I simply took the average of each of those treatments at actually we looked at mostly every day, an average of every day. So this was on a much finer time scale than every day. But to analyze this and to look at really the broader picture, we only looked at daily averages. Next slide is just an example. It's not just an example, it's actually a summation or summary of all these treatments in 2018. So 2018 and 2019 were quite different, especially for what happened in May. In this particular case, we're looking right now from, I don't know if you can see my cursor on your screen. We're looking at mid-April through about the 20th of May. At which time where there was an irrigation. That was something the grower did, not necessarily something we called for, but it was there nonetheless. And so we had to look at this in that context. So we're looking at essentially at 2 different drying periods, from April through mid-May, and then again after this was irrigated, and then through mid-June. And these are the 3 treatments we're looking at. I tried to keep the color codings similar, well, exactly the same. So the orange treatment is the full till treatment, the gray one is the no-till treatment, and the blue one is the alternate row till treatment. I also noted here when the treatments were imposed and where practices were imposed. So these treatments were tilled at this date. It's not really pointing at any one of the treatments, but kind of late April, these treatments were imposed. And then they were mowed for the second time, because the first time it was before this chart, middle of May. Now, I just found out recently when these treatments were imposed, because that makes a little bit of a difference on my analysis. I'm going to have to do some reanalysis of this data because effectively, they should be analyzed from this point forward instead of back here. I analyzed from back here through here. But since the treatments were imposed here, it's going to make a little bit of a difference on my analysis. So let's put a little bit more weight on this one, because this second drying period here is when all the treatments had been imposed. They had been mowed. Everything was kind of dressed up. So I'll put a little bit more weight on that side of, or that time period than I will the first. Now, this is the 30 centimeter depth, or 1 foot depth. I'm going to show you the 60 centimeter depth also, but first I'm going to show you 2019. In 2019, it was a little different. This is, again, the 1 foot depth, 30 centimeters. And this is when the treatments were imposed. They were mowed here and they were tilled here, late April. And then they dried down. And then we had that horrible rainfall, middle towards the second or third week in May. And it was substantial, as you all know. Rained about 4 inches or so. Okay, and so we also had a nice dry down period. I like to look at this one better than 2018, because the first one was an irrigation, and the irrigation was done under the vines, but when it rained, it was covering everything. So I like this, actually like the 2019 data set better, just because of the weather was more friendly. I don't want to look at too much of these wiggles. There are some wiggles you can kind of look at after they were mowed and tilled, but and I don't have time to discuss it all. I also plotted ET, or relative reference ET, here at the bottom, just to see what might have also influenced the water uptake. But just so you know, and just so you look at these, this is relative water content on the x-axis, so more wet, drier, and times on the x-axis. I should have said that already. But in case you didn't know, this is relative water content. So as time goes by, the soil dries out, which is what we expect. This is, again, 2018 at the 1 foot depth. Not going to go into it because I don't have enough time to go into it. Eventually, this will show up in print, so you'll be able to look at it. And this is the 60 centimeter depth in 2019. What I wanted to do, though, is analyze this from a little more quantitative standpoint than just looking at charts. So we looked at the rate of depletion. So simply, how much percent relative water content per day is affected by these treatments. And so we looked at this period here, and we looked at this period here. You see how it kind of flattens out later into July? I didn't look at that. I only looked through about mid-June. So really when the initial depletion occurred, and then as they flattened out, that means the water content is going down substantially, and the vines aren't taking as much water at those levels. I don't know if you can see, these are kind of small on my screen anyway, but these are just some bar charts of relative water content per day depletion rates. So the higher the bigger the bar, the faster they are depleted. And over here we have the 1 foot depth, and down here we have the 2 foot depth. And so over here we also have the early period before the irrigation and the late period after the irrigation. Again, I like to focus on this one because I think it was more truly analyzed. We do see a difference, and this doesn't make a lot of sense. The alternate row tillage actually had a lower depletion rate than the other two treatments, the no-till and the full-till, both have about a similar rate. And in the 1 foot depth, they're much similar, with the no-till being a bit higher in water rate depletion than the other two treatments. 2019 is the year I like better as far as the analysis goes, because of the rainfall event that we had. And again, you see something completely different. So that is frustrating for analysis, but it is what it is, and we have to look at it. But if we focus on the late season, you see that, or not the late season, but the post-rain period, you see that the no-till treatment at the 1 foot depth had a lower rate of depletion than the other two treatments. But at the 2 foot depth, at the 2 foot depth, it actually had a higher rate of depletion than the other two treatments. I thought that was pretty interesting. Now, I wanted to quantify a little bit more. This is a chart of the rate of depletion. It's really essentially those bar charts shown in tabular format. And where I put the green highlighting, it's essentially to show the treatments, or treatments during the periods that had the lower depletion rates. And it's a little bit all over the map. So you see that, and I won't go into this in a lot of detail. I have like a minute to talk. The no-till treatment in 2019 had a lower rate of water depletion in, I'm sorry, at the 1 foot depth, but a higher rate of water depletion at the 2 foot depth. And to further simplify this, and to come to some kind of conclusion, I took out the alternate row treatment. Alternate row is a little bit, I call it a tweener. It did behave like both, but wasn't really consistent. So I just compared the full till to no till, and there are some trends here. And if you combine the 2 years, which is what I did down here, you do see what I just told you, that the no-till treatment had a lower rate of depletion at the more shallow soil depth, but a higher rate of depletion than the full till at the 2 foot depth. And if you combine these two depths, 30 and 60 centimeters, you really don't see any difference. I think that's the take home. And that's kind of, I'll jump to the conclusion there for a second, but really the take home is you have a higher rate of depletion with tillage in the upper portion of the profile, but you have a lower, but you have a higher rate, lower rate of depletion down below. They pretty much average out to be a wash. At least in this trial they did. Again, it was only a 2-year trial, so not as exhaustive as Patty's talk or project. So I'll just jump to a few conclusions. I'm going to be out of time. I'm out of time. I got another minute. The differences were inconsistent, as we kind of expect with only 2 years of data. I'd love to do this more, but we don't have any funding to do it more, but it's still interesting. There were different effects at the 1 and 2 feet levels. The full till treatment had a higher rate of water loss in the upper foot. And the way I'm thinking about that, we talked a little bit about dust mulching and that kind of thing. Well, you're disturbing the soil, you're going to make it warmer when you have less vegetation on it. And you're disturbing it, it's going to evaporate at that shallow depth more than likely. But we seem to have, it seemed to protect the lower depth. So because the lower rate, there was a lower rate of water loss in the 2nd foot with the full till treatment. The no-till treatment was just the opposite. Okay, we had a lower rate of water loss in the upper foot, but a higher rate of water loss in the 2nd foot. You can come up with a lot of theories here, and maybe I will. I definitely will when I write this up. But for now, it's interesting that it was, if I saw any consistency, it was just that. Now, the alternate row tillage behaved like, I call it like a tweener. It's between the two other treatments. The early spring, it behaved like the full till in the upper foot, and was sort of between the full till and the no till in the lower foot. Now, late spring, when I say late spring, is after the rain or after the irrigation. It behaved like no till in the upper foot and like full till in the lower foot. And I think alternate row tillage is probably the most commonly practiced in viticulture in the North Coast. You have to think about some of the physics involved with the tillage. It's going to create that warm soil in the rows that are tilled, whereas there's vegetation in the other row, and that's going to have an influence, a cross influence, because the tillage is going to create a warmth and raise the temperature at the floor level, and that's going to advect over to the other treatment as well, and potentially create even more transpiration from the cover crop or from the vines. Just speculation. So, but combined upper and lower foot, we really saw no net effect. So that's really my conclusion from this 2-year study, is that there was very little difference in soil water depletion between the tilled and the non-tilled treatments. I guess that's kind of interesting, because I've always thought that tillage would conserve moisture, but in this case, it didn't show that overall. And that's all I had. Thanks a lot.
We've got a couple questions for you. Was there a tool station on site?
No, Julie? No.
Julie, yeah.
No.
Okay.
There had been the first year, but not the second.
And then they want to know whether the deeper soil moisture rate of depletion related to the soil giving up some moisture to feed the vines.
The deeper soil moisture depletion?
Mm-hmm.
Yeah, definitely. I mean, definitely, probably, since we have to speculate here. And our treatments were imposed in the middles, and we're measuring under the vine. We're not exactly measuring the direct effect of the cover crop roots. We're measuring the indirect effect. And so there's all kinds of ways we could look at it. But tillage, we saw the bigger effect in the shallow upper foot. And there's some roots in the upper foot, but I think most of the vine roots tend to be in the 2nd foot. That's probably the highest density of roots in the 2nd foot. So when we tilled, we did see that greater loss of water in the upper foot. Some of that could have been from vine uptake, but a lot of it could have been from directly evaporation from the surface. Hard to tell without really doing measurements in the vine row and the middle to know the difference.
And then the final questions around the duration of the study. So what would be your preferred length of time to really draw conclusions from it?
As much as possible, I'd say 5 years would be a really nice period of time. You know, Patty's study was many, many years, and that's really ideal. The more the better. I'd say 5 years would be ideal. Would be a nice compromise, but it's not very practical. You know, for most of these studies, you just can't go that long.
All right, well, thank you, Mark.
Thanks a lot.